Hi, welcome back to another video. In this video, we'll continue to look at 16E, position and average velocity. So if you have a curve, you can always find 2 points on this curve. And if you draw a straight line that passes through both of them, and you know the coordinates for these 2 points, using right over run y2 minus y1 over x2 minus x1, you can find the gradient of this linear graph, and this will be the average velocity in a time versus position graph. So this is what we did in the previous video. In today's video, we'll look at how to draw velocity versus time graphs, and we're actually going to draw this based on time position graph. So what is piecewise defined function? This is a new term. Piecewise defined function means it's hybrid. It's a function defined by multiple subfunctions, where each subfunction applies to a different interval in the domain. So if you have a graph that looks like this, so you have different straight lines, different linear functions, then this is called a piecewise defined function. So here's an example. This is a piecewise function, by the way. Okay, so the question says, the graph shown is the position time graph for the bicycle trip of a boy who lives on a long straight road. The road runs north-south, and north is chosen to be the positive direction. Remember before we said moving to the right is positive and moving to the left is negative. So in this case, instead of going to the right or left, we're talking about up or down, but it's the same thing. So going to the north is positive and going to the south is negative. And question A says, describe his trip. Okay, so let's draw it out. So let's say he started at point O, which is his house. So he's traveling to the north. Okay, so he started at his house, and 2 hours have gone by. The boy went for 20 kilometers. So that's his initial position. After 2 hours, he traveled 20 kilometers. And let's say he stopped at a park. Okay, so this is park 1. So this is actually point A, and his motion is defined by this straight line. And then he traveled back. So from here, he's traveling back. But he didn't stop at his house, which is his initial position. So he didn't stop there. And he rode past his house and didn't stop. He traveled another 10 kilometers, and let's say he went to another park. Okay, so here's another 10 kilometers. And here it has to be 20 kilometers because he needs to cover the same distance. And let's say he stopped at park 2. This is also our point B on the graph. And this x-intercept, this yellow point, corresponds to this point there. So this is when he traveled past his house, but he didn't stop. After 1 hour, he went back home. Sorry, he traveled another 10 kilometers and he's now reached home. And this final point is point C. So after 5 hours, he finally reached home. So I think we've answered question A already. So we described his trip. We can now find the average velocity. So the boy heads north for 2 hours. This was described by this orange line here. His initial position is 0, 0. So at time 0 hours, he traveled 0 kilometers. That's our initial position. After 2 hours, he's now 20 kilometers away from point O. Using these 2 coordinates, point O and point A, we can find the gradient, which also happens to be the average velocity in this case. So 20 minus 0 over 2 minus 0, which is 2, that's going to be 10 kilometers per hour. And does this make sense? Yes, because he heads north, and north is defined as the positive direction in this case. So the average velocity will also be a positive number. And he then turns and rides south for 2 hours. This was defined by this green line. Again, this is our y2, this is our y1, minus x2 minus x1. The gradient, or the average velocity, is going to be negative 10 minus 20 over 4 minus 2, which is 2. The average velocity turns out to be negative 15 kilometers per hour. Now, don't let this confuse you. Although we have graph both above and below the x-axis, but since we are traveling in the opposite direction, so that's why the average velocity is negative. Because once he reached point A, so park 1, he heads back. and that's when he's traveling in the opposite direction. So since we're traveling in the opposite direction, the average velocity will be negative. Finally, he turns and rides north until he reaches home. So that's defined by this blue line here. And we want to find the gradient of this blue line. We know the 2 points, rise over run, that is equal to 10 kilometers per hour. And as you can see, although this part of the graph is below x-axis, but it's going to be a positive average velocity because we are heading north, which is defined as the positive direction here. Question B says, draw the corresponding velocity time graph. Remember, since this is a piecewise defined function, each section of the graph has different gradient. And having different gradient means they have different velocity. Okay, so velocity and time graph is something new, but we've pretty much calculated everything in question A. So we can just use the information we just obtained to plot velocity time graph. On the horizontal axis, we have time, and vertical axis becomes velocity. Okay, so the boy heads north for 2 hours. Since the average velocity during this time interval is 10 kilometers per hour, and he's heading north, which is defined as the positive direction, so the graph is above x-axis with a vertical value 10. And then during the green interval, he's traveling at 15 kilometers per hour, and it's in the opposite direction, so it's a negative average velocity. That's why it's below x-axis at a vertical value negative 15. And finally, he turns and rides north until he reaches home. So we're traveling in the positive direction again with an average velocity 10 kilometers per hour. So this blue portion here from t is equal to 4 to t is equal to 5 is 10 kilometers per hour. Okay, question 15. A particle is moving in a straight line. It was initially at rest at point O. It moves to the right of O with a constant velocity and reaches the point A, 15 meters from O, after 5 seconds. It then returns to O. The return trip takes 10 seconds. It stops at O. On the one set of axes, draw the position time graph and the velocity time graph for the motion. Okay, so this question is actually easier than the previous one, but it's trickier in a sense that we're plotting the 2 graphs on the same set of axes. So you've got to be careful with that. So it's initially at rest at point O. This implies our starting point is O, 0, 0. So as labeled here, this is our starting point. It moves to the right of O with a constant velocity and reaches a point A. Let me use red. Okay, so it's moving to the right until it reaches point A. Okay, 15 meters from O. This implies the vertical value is 15. And this was after 5 seconds. So the horizontal value t is 5, and the position, I'll use x, is 15 meters from O. So this gives us point A. After 5 seconds, when t is 5, the position is 15 meters to the right of O. It then returns to O. Let me use green. The return trip takes 10 seconds, it stops at O. So 5 seconds have gone by, we reached point A. And once we reach point A, we're going to return. And if the return trip takes 10 seconds, so this means the time when we finally reach point B, okay, our final position will be 5 plus another 10 seconds, which is 15. So 15 seconds have gone by, we finally stopped at point O, and we reached our final position, which is point B. So when time is 15 seconds, we're back to where we started. So this is how you plot time versus position graph. What about the time velocity graph? Clearly this is a piecewise defined function again, and we have 2 linear functions. The first one is this red one, maybe I'll label this as 1, and the second linear graph is our return trip. And we know 2 points on each line, we can calculate the gradient for these 2 lines. Since this is a time versus position graph, the gradient will be the average velocity. Okay, so for linear function 1, the average velocity is going to be 15 minus 0 over 5 minus 0, which is 15 over 5, which is 3 meters per second. And the average velocity for our return trip is going to be 0 minus 15 over 15 minus 5, which is negative 1.5 meters per second. Now we know the average velocity. 3 meters per second is a positive average velocity, so that means we are traveling to the right. So for the time interval 0 to 5, the average velocity is going to be 3 meters per second. So you just need to draw a straight line indicating your average velocity in this case. For our return trip, the average velocity is a negative number. So that's why it should be below x-axis. So for the time interval t is 5 to t is 15, we're traveling at an average velocity of negative 1.5 meters per second. And this implies that we're moving to the left of O. That's why it's a negative average velocity, and also the velocity graph is below x-axis. Okay, last example. The position of a particle moving in a straight line is given by the function s of t is equal to t cubed minus 6t squared, where t is greater than or equal to 0. The graph of s against t is shown. The corresponding velocity time graph is also shown. The function describing the velocity is v of t is equal to 3t squared minus 12t. Just a recap, average velocity is equal to s2 minus s1 over t2 minus t1. Okay, so it's essentially the gradient. The first graph is time versus position. The second graph is time versus velocity. So make sure you know which is which. Question A says find the average velocity of the particle for the intervals. Here the question is giving us the t values. So t1, t2. To find the corresponding position, we're going to sub in these values into our position function. So at t1, the corresponding position is going to be s of t1. And at t2, the corresponding position is going to be s of t2 over t2 minus t1. And in this case, so 4.5 minus 3.5 is 1. And pretty sure you need a calculator for this question. So if you plug in the values, the average velocity turns out to be 0.25 meters per second. Second question, third question, we're doing the same thing. So we're plugging the values to find the corresponding position and finally work out what the average velocity is. As you can see, the 2 points we're taking are getting closer. So that's why the difference in t values are getting smaller. So from 1 to 0.2 to 0.02. This implies that we're obtaining a more accurate estimation here. Okay, question B says from part A, what's the instantaneous velocity when t is 4? Since the question has given us time velocity graph, we can just look at the velocity when time is 4. So when time is 4, the instantaneous velocity is 0. So why is it 0? So if you think about it this way, okay, so here's our starting point. We're traveling, I think we're probably traveling to the left first because the majority of the graph is below x-axis. So traveling to the left, and then this is a turning point. We're turning around here when time is equal to 4. Okay, so after 4 seconds, we are traveling back to point O, which is this x-intercept here, but we didn't stop. We continue going. So the orange part is the graph that's above x-axis. The instantaneous velocity when t is 4 is 0. That's because we are at this point when we're turning around. So think about this. If you walk to the left and then you want to walk to the right, you need to turn around, right? So think of this as that instant you are turning around. So at that very moment, you're not moving yet. You're just turning around. You don't have a velocity. So at that very moment, the instantaneous velocity is 0 because you're not moving. And question C says, for what values of t is the velocity positive, and for what values of t is the velocity negative? So think of Spidey. It can be saying that the velocity is positive when t is greater than 4. So that's when the Spidey is climbing up the curve. And the velocity is negative between 0 and 4. That's when Spidey is sliding down. So I really hope this video helps, and I'll see you in the next video. Bye!